Welcome everyone. Today's seminar covers tuning machine models with complex storage mechanisms, a key topic in theory of computation. We will examine how extending the standard tuning machine storage through multiple taps, tracks, heads, and non-determinism deepens our understanding of computational power and efficiency. The primary reference is Hopcroft, Motwani, and Ullmann's Introduction to Automata Theory, Languages and Computation, 3rd edition. This presentation is designed for a 12-minute delivery and carries 16 marks. Alan Turing introduced his machine in 1936 to address Hilbert's problem. The tuning machine consists of an infinite tap divided into cells, a read-write head, and a finite control unit. It reads symbols, writes new ones, moves left or right, and changes states based on a transition function. Despite its simplicity, the tuning machine captures the essence of algorithmic computation and serves as the theoretical basis for all modern computers. The Church-Turing thesis asserts that any effectively computable function can be computed by tuning machine. Understanding storage variations is crucial because the way a tuning machine accesses and organizes memory directly affects time and space complexity. Even though all variants remain computationally equivalent to the standard model, components of standard tuning machine defined as a 7 tuple q sigma torque delta q naught b f q states sigma input alphabet പിന്നെ torque type alphabet delta transition function q naught start state b blank symbol f accept states. Single tap and single head serve as the basic model. Limitations of single tap tuning machine: computationally powerful but often inefficient, requires frequent tap traversals. Example, palindrome checking takes big O of n square time. Cannot access multiple locations simultaneously. Motivates advanced storage models. Complex storage refers to any extension of the standard tuning machine's memory mechanism that provides additional structural capabilities. The key insight from computability theory is that all these variants, multi-tap, multi-track, multi-head, and non-deterministic tuning machines, recognize exactly the same class of languages, the recursively enumerable languages. However, they differ significantly in time and space complexity. For instance, a multi-tap tuning machine can simulate a single tap tuning machine with at most a quadratic slowdown, but the reverse simulation can be exponentially slower for certain problems. This makes complex storage models essential for studying complexity classes like P and NP. The motivation is both theoretical and practical. Theoretical means understanding the hierarchy of computational resources. Practical means designing more efficient algorithms. In multi-tap tuning machine, the finite control reads symbols from all k taps simultaneously and writes to all of them in a single transition. The transition function maps a state and k inputs to a new state, k output symbols, and k head movements. Tap 1 typically holds the input read only, while subsequent taps serve as workspace. The simulation theorem states that any k-tap tuning machine running on time T of n can be simulated by a single tap tuning machine in big O of T of n square time. This quadratic overhead is tight for certain problems. A classic example is palindrome recognition. The multi-tap tuning machine copies the input to a second tap, reverses it, and compares both taps in linear time, whereas the single tap version requires repeated back and forth traversals. A multi-track tuning machine uses a single tap where each cell is subdivided into k tracks. Think of it as a spreadsheet where each column is a track and each row is a tap cell. The head reads all k symbols at the current position simultaneously and writes new symbols to all tracks in one step. Formally, the tap alphabet is the Cartesian product of k individual alphabets. This model is particularly useful when the machine needs to store auxiliary informations such as marks, counter, or intermediate results directly alongside the input. For example, one track can hold the original input while another track stores processed data. The multi-track tuning machine is computationally equivalent to the multi-tap tuning machine. Any k-track tuning machine can be simulated by a k-tap tuning machine and vice versa with only linear overhead. The multi-head tuning machine places two or more heads on a single tap. Each head can move independently, allowing the machine to scan different regions simultaneously. For instance, one head can anchor the start of a string while another scans forward, eliminating repeated traversals. This is particularly effective for pattern matching and string comparison problems. The non-deterministic tuning machine extends the transition function to return a set of possible moves rather than a single move. At each step of non-deterministic tuning machine branches into multiple parallel computations. A string is accepted if at least one branch reaches an accepting state. Non-deterministic tuning machines are central to complexity theory. The class NP consists of languages decidable by an non-deterministic tuning machine in polynomial time. Both models are tuning equivalent to the standard tuning machine but offer significant time complexity advantages for specific problem classes. The table summarizes the 5 tuning machine variants we have discussed. Note that all models recognize the same class of languages, the recursively enumerable languages. Confirming their computational equivalence, the differences lie in efficiency and structural convenience. Standard tuning machine is the simplest baseline. Multi-tap tuning machine provides true parallel access to multiple taps. Multi-track tuning machine stores structured data in a single tap cell. Multi-head tuning machine reduces head movement overhead on a single tap. Non-deterministic tuning machine enables branching computations, forming the theoretical basis for NP completeness. When choosing a model for analysis, select based on the problem, use multi-tap for time complexity proofs, multi-track for structured data problems, and non-deterministic tuning machine for NP class analysis. Complex storage models have wide-ranging applications. In algorithm design, multi-tap tuning machine helps establish tight time complexity bounds. In complexity theory, non-deterministic tuning machines defines the class NP and are central to understanding NP completeness. Compiler designers use multi-track concept to model parsers that simulate simultaneously track input tokens and grammar states. In AI, non-deterministic models inform heuristic search and parallel computation strategies. To summarize, we explored 5 complex storage variants: multi-tap, multi-track, multi-head, and non-deterministic tuning machines, all computationally equivalent to the standard tuning machine but differing in efficiency. These models bridge abstract computation theory with practical computing architectures. Thank you for your attention. I welcome any questions.